Hello and welcome to part 3 of the video tutorial for the 2009 electricity paper. And this is part 3, which is all about magnetic fields and magnetism. So Sean's yacht has an 8-meter high mast with a light on top, we can kind of see here. 2 wires connect the 12-volt battery to the lamp, nothing else is connected to the battery. So the total resistance, I don't know if you can see that, the total resistance of the wires in the lamp is 18 ohms, and the horizontal component of the Earth's magnetic field is 4.10 to the negative 4 Tesla, and obviously we have the charge of the electron as well. And I think now is probably a good time to go through and label this. So if we have a look at this, they're giving us the voltage, they're giving us the length of the mast, they're giving us the resistance, they're giving us the strength of the magnetic field, and they're giving us the charge. So we have 5 variables already given to us, so we already know what all of those are, so this should make the calculations a lot easier. So there's the picture, and we have these crosses mean that the magnetic field is coming towards us like this, if you can see my pencil. That's what it means. So we need to state the direction of the magnetic force acting on the wire that is connected to the terminal of the battery. So I'm going to try, you can use the right hand rule for this, or whatever version of the XYZ thing you're using is. So I'm going to try and show you now. So we have the mast which is going this way, and the field which is coming towards us like this. And that means that the magnetic force is going to be coming this way. So it's going to be coming to the right. So to the right. And we need to calculate the size of the magnetic force acting on one wire. And the reason they're telling us one wire is because there's going to be one wire traveling in each direction here, so it's, as we see here, the wires. So we just need to find what one of them is. I think one of the other questions will probably do something about the other wires, so we'll come back to that. But all we have to focus on is calculating the size of the magnetic force for now. So here's the formula sheet again. And we'll be using this one here. This is magnetic force, which is equal to the magnetic field times the current times the length, which is the length of the mast in this case. So that's F. The magnetic force is equal to the strength of the magnetic field times the current times the length. Now we have the voltage and the resistance here, but we don't have the current, so we just need to quickly work out the current. The voltage is 12, and the resistance is 18 ohms. So we know that I is equal to V over R, which in this case is equal to 12 over 18. And this is the same as 2 over 3. And so now we can just plug everything in. We've got the strength of the magnetic field, which is 4 times 10 to the negative 4, and the length, which is 8 meters. So this F is equal to 4 times 10 to the negative 4 times 2 over 3 times 8, which is equal to 10 to the negative 4 times 2 divided by 3 times 8. Okay, so that's 2.13, or what should we round that to? 2.1 is going to be the right number of significant figures, I think, because I didn't put them in here, but this is actually 8.0, and these are all given to, well, the voltage isn't, but the resistance is given to this. So the right number of significant figures is just going to be 1, so we'll just have 2.1 times 10 to the negative 3 to the negative 3, so that's the magnetic force. will the magnetic force on the two connecting wires produce a net force on the yacht? Explain your answer. So if we have a look at this again, we've got each wire is connected in a different direction, so we've got one which is going up like this, and then another which is going up like this, but they're traveling in different directions, so that one's going up, that one's going down, or maybe it's the other way around, but we've got different directions of the current and everything. So the force is, what's the question? Will there be a net force? So there won't be a net force because the forces are going to be balanced, because the forces will be the same in each direction. So there will be no net force. No net force. As the wires carry current in different opposing directions. Therefore, oh sorry, you probably couldn't read that. Therefore, the forces balance out. Okay, so the yacht now moves forward, and Sean switches the light off. Is there voltage induced in the wire as the yacht moves forward? So I think what this means by he switches the light off, I think that means that there's, if we have a look at this, I think that means we can effectively ignore the voltage and resistance, because there's no longer anything active in the circuit. But if we have a look at the formula here, this is the formula for induced voltage. All we need is the length of the mast, which we have. The strength of the magnetic field hasn't changed. That's the magnetic field, the horizontal component of the Earth's magnetic field. And now we have velocity, and we didn't used to have velocity because the boat or the yacht was stationary, but now it's moving, so we can calculate this. So V equals BVL. Is there induced voltage in the Y as the yacht moves forward? So yes, there will be. We can say V is equal to BVL, and there is a magnetic field present. Oops. Which the mast is moving against, or which the mast and the wires. So all three components required to induce voltage are present. And now what we have to do is calculate the size of the magnetic force acting on a single electron if the yacht moves at 3 meters per second perpendicular to the magnetic field. So this shouldn't be that difficult if we have a look at our formula sheet. We've got the one formula here, which is, and this gives us the magnetic force, but this gives us the force acting on the electron. So F is equal to BQV, and the charge Q is given to us. Oh well, hopefully you should know by now that that's. Well, you don't need to know it, but Q is equal to 1.6 times 10 to the negative 19, and this is actually negative, but it doesn't make a difference for these calculations. We know B is equal to, and this is the magnetic strength of the magnetic field, is equal to, 4 times 10 to the negative 4, and the length, oh no, sorry, the velocity is given to us here, which is 3 meters. So this is just going to be F is equal to 3 times 1.6 times 10 to the negative 19 times 4 times 10 to the negative 4. So if we just put this in the calculator, this will give us 3 times 1.6. So that's 1.9 times 10 to the negative 22. And this is in newtons. And that's the last question in the exam. I hope that was useful and I didn't confuse you too much in the earlier parts, and I'll see you soon.